Well, thank you very much, and thank you for inviting me here. It's on the one hand, I feel greatly honored to give the sort of closing lecture of this conference, and I should also say it's, as always, immense pleasure to be here. And I really regret that I couldn't take part in previous part of this conference, because even from what filtered through from the questions and allusions to previous talks, it sounded really intriguing. After some consultation with Thibaut, I've decided to give a more general talk, so I apologize in advance to those of you who are really specialists. Certainly string theorists will not learn very much from this talk. As I said, it's going to be a brief survey. It will be rather pointillistic, I would say, in the sense that I will just touch on a few things and make a few remarks, and they will also not cover everything, but it will certainly take the liberty to spend a last part of my talk on things that are very close to my heart when it comes to what a potential theory of quantum gravity could be. So I would like to start out by recalling the reasons why we should be interested in a theory of quantum gravity, because at this time there's actually no pressing need from any experiment or observation to really proceed in this direction, because the theories that we have at this time seem to be working extremely well. This applies both to general relativity but also to the standard model of particle physics, which gets better and better with every measurement. So the reason to be, nevertheless, to be interested in the theory of quantum gravity comes from basically the fact that the two theories that we have are incomplete and possibly even inconsistent in the ultimate consequence. On the general relativity side, it's the issue of singularities, which seem to be generic. This follows from the singularity theorems that were proven by Hawking and Penrose a long time ago, according to which generic initial conditions, like they exist in our universe, will inevitably lead to singularity formation. And of course, there's the cosmological singularity, the Big Bang singularity at the beginning of our universe, and this is the greatest puzzle. In some sense, this is what we really would like to understand. I mean, one of the amazing stories of modern physics that with the understanding we have, we can get very close, like 10 to the minus 30 seconds or so to next to the singularity, but it's just this tiny little bit that causes all our headaches. And of course, there's the question of structure of space-time at the smallest distances. On the other side, in quantum field theory, there as well, we are faced with some, lurking inconsistencies, possibly. So as you all well know, in perturbation theory, we encounter ultraviolet divergences in Feynman diagrams. For the standard model symmetries, these can be removed by infinite renormalizations, order by order. This is a rather sophisticated procedure that has been developed over decades, actually, and has led to amazing agreement with experiment. If you think about things like G-2 or now precision experiments they're now doing for the electroweak theory, but nevertheless, I think Costas showed this, or quoted Dirac on this, who never accepted infinities. He said the right theory should give finite answers, period. So we're not really sure, or we somehow feel that this cannot be the end of the story. And in some sense, you can make it a little more precise, because you can ask yourself, if you want to go beyond perturbation theory, does the standard model, which works so well in perturbation theory, does it make sense beyond perturbation theory? And I think there's now some reason to believe that it will probably not exist in the rigorous sense of constructive or axiomatic quantum field theory. And this is the reason why people are talking about there's a possible ultraviolet completion of the theory, there is some other theory that contains the Standard Model as a limiting case. So the difficulties in both cases, in some sense, may have a common origin, because in both general relativity and quantum field theory, we treat space-time as a continuum or differentiable manifold, meaning that we can, in principle, should be able to go as small distance as we like. And secondly, in certainly quantum field theory, so far we treat elementary particles as mathematical points, exactly point-like excitations, and this is of course the origin of these ultraviolet divergences. But there's also a difficulty when you try to describe point particle mechanics in general relativity. So the conclusion of all this is, at least a majority of the community believes in this, and this is independent of whether string theories or loop quantum gravity. You expect something dramatic to happen at the scale at which we believe quantum gravity might be relevant, which is the Planck scale. So the question is really what happens, how are these theories modified, what happens to continuum space-time? Is it sort of dissolved in a kind of discretuum? Is the continuum replaced by a discretuum? Or what is it that, or maybe it's non-commutativity of space-time coordinates, but something is expected to happen at this scale. So this is the relevant scale that we're talking about.
Hopefully something will be found before that scale, otherwise.
Well, we'll have to, and now, with regard to, once you accept this point of view, that you can adopt two different kinds of attitudes. And this also marks the dividing line between the different approaches to quantum gravity. One hypothesis is that quantum gravity essentially is just a non-perturbative quantization of Einstein gravity in whatever formalism, metric, connection, loop, discrete. And once you solve this and treat it suitably, you just have to complement this theory by the Standard Model of particle physics. And that this together then correctly describes the physical degrees of freedom, also at the very smallest distances. The opposite hypothesis is that actually general relativity is just an effective or low energy theory arising at large distances from a more fundamental Planck scale theory. And that we do not at this time know what the basic degrees of freedom of these theories are, except that we suspect they're very different from either general relativity of quantum field theory as we know them. In this case, general relativity, and with it space-time covariance, such notions of space-time general covariance are assumed to be emergent, much like macroscopic physics emerges from the quantum world of atoms and molecules. And from this point of view, this first approach would seem as sensible as trying to find out about the microscopic world by, say, applying quantization techniques to the Navier-Stokes equation. I mean, everyone would agree that it's very unlikely that you would find out about atoms and molecules in this way. Now, a basic fact about quantum gravity that sets, or quantized gravity that sets it apart from the matter interactions that characterize the Standard Model is the fact that gravity, Einstein theory, is perturbatively non-renormalizable. This means that at each order, in order to get sensible results, we have to introduce a new kind of counter term to render the theory predictable and finite. So here's the famous two-loop counter term whose coefficient here was calculated some 30 years ago. So but I should like to emphasize, it's not just the fact that you have divergences, because you might think, well, let's subtract them and make the theory finite. It's the fact that you need to adjust an infinite number of parameters, and this is believed to render this theory non-predictive. Because then, if you have an infinite number of coupling constants, there's no chance to pin down what the theory is. Again, there are two possible conclusions in line with what I said before. The first conclusion is that somehow you have to, consistent quantization of gravity requires that we need to introduce a radical modification of the theory at very short distances. in particular include matter, supersymmetric matter, fermions, and maybe even something more radical, like going from point to particles to extended objects like string or membrane theory, and thereby to get rid of this divergence. The opposite point of view, also expressed most colorfully, I would say, by Roger Penrose, is that actually the ultraviolet divergences are simply an artifact of perturbative treatment of the theory, because when we do perturbative quantum gravity, we do some violence to the theory. We destroy somehow the geometrical structure, general covariance. All of this is no longer there in a nice and manifest form, and therefore the hypothesis is here that these would disappear upon proper non-perturbative quantization of the theory. However, and this is something whatever your attitude towards this is, I think no approach to quantum gravity can claim complete success that does not explain in full, gory detail what happens with this divergence. Now, this is easier for approaches that start from particle physics, because there one somehow tries to get rid of the divergence right directly. But this comment applies more to the non-perturbative approaches, because sometimes they say they don't even see the divergence. I just want to say, if you claim you don't see the divergence, then I think that you need to investigate your approach a little more closely, because whatever your non-perturbative approach is, it should admit a semi-classical limit, and then once you do this, then this thing will reappear. So there's no way around. Anyone who claims to have a theory of quantum gravity and does not explain to me what happened with this divergence will not. I will not accept this as an answer.
Are you sure you want two negations? No, it's not, because it means the contrary of what you want. Yes. There are too many
found
negations.
mistake in your English.
Sorry. You mean double negative. Sorry. Now, there's also the thing about gravity and matter. This is what Einstein himself said about his equation. He said the left side is built from marble, beautiful, unique. The right-hand side, he said, is made from timber. This is the energy momentum tensor of watt, dust, whatever, standard model, T mu nu. So he spent a good part of his later part of his life trying to see whether he could understand this in a geometrical way. So the wish would be to somehow write the right side, bring it to the left side, and somehow understand it as some kind of.
Wouldn't you agree that it's the other way around, actually? The left-hand side is the hydrodynamics and the right.
Timber, and this is the marble.
Yeah.
You mean the opposite of what Einstein said?
Yeah.
Depends on taste.
I think, and on this I would side with Einstein. Anyway, this has led to an enormous effort over the past decades, really. For example, Kaluza-Klein theory is an attempt in this direction, when you take the theory in higher dimensions and explain the matter energy momentum tensor as coming from higher dimensional geometry, so in part sort of going in this direction. And the other thing is that you can introduce supersymmetry, which is like introducing fermionic coordinates, and they're also enlarging your space-time, and then also endowing this right-hand side with a kind of geometric interpretation. There's also the question of gravity versus not quantum field theory or quantum gravity, but just standard quantum mechanics, because we have this kind of schizophrenic, Slava would probably say, situation where this is treated completely classically, and this should really be thought of as a quantum object or expectation value. And this has also led to a long debate. In particular, the question is whether we need to change the basic rules of quantum mechanics, as was suggested originally by Hawking. For example, should we really allow for the possibility that pure states can evolve into mixed states? And the other thing I would like to mention here is that, because after all, at least my favorite approach, space and time are somehow thought to be emergent. And so you should start out with a theory that does not have space and time. And then I would just like to emphasize that many of the paradoxes that we think occur in quantum mechanics appear in a completely new guise, because most of these paradoxes have to do with non-locality, and there you really need some notion of space or maybe even time in order to make sense of it. So the whole question, I just want to raise it, not answer it, is if you're really in a sort of pre-geometrical framework, what is this a different question now, or how should we address it? Finally, the final point is the so-called hierarchy problem, which is the fact that gravity is so much weaker than the other forces. In my popular lectures, I illustrate it by taking a pin and a little magnet, and then the pin is drawn towards the magnet, and then I say, you know, this little magnet beats the gravitational pull of the whole planet. And this is a rather direct evidence of this hierarchy problem, namely that the scales are so much different. So in particle physics, we talk about the masses. We actually cover a wide range. So you already here have something like a little hierarchy problem, but all of this is tiny vis-a-vis the Planck scale of 10 to the 19 GeV, which is the equivalent of 10 to the minus 33 centimeters. So a key challenge, and perhaps the crucial issue in this whole game, is for any proposed theory of quantum gravity, is that you should offer quantifiable criteria to confirm or falsify the theory. And in particular, they should be such that they allow to discriminate your ansatz from somebody else's ansatz. You know, there's not much is gained if, some theory that explains structure formation or whatever. There will be many theories or things like hypothetical things like violations of Lorentz invariance. If this was really seen, there will probably be many, and in fact, conventional explanations of such facts. So I think the challenge is here much more pronounced. And of course, you can always say, my objects are quantized in units of the Planck length, but this is something that we will never be able to measure. So here, some degree of sophistication is required. So here is a list of the approaches, not complete. I would say that, roughly speaking, the community is divided into a majority part that does a string theory, supergravity, and so on. There's the more path integral is something in between. There's canonical quantization, loop quantum gravity, out of which we develop the modern discrete approaches like spin forms, group field theory, and so on. But apart from this, we also have non-commutative geometry. We have something called asymptotic safety. And then you can go even more abstract in the sense that you could even look for a theory where everything is just information theory. And I should say, there's no agreement. It's really that we have different communities, in fact, with very little communication. And Jörg showed this different picture, but this is the same event, historical event. And as you know, this event or this effort failed because at some point people could no longer communicate with each other. And this is something I also see happening a little bit in the different communities working on towards quantum gravity. And I think if you're sort of zeroing in on the right theory, we should see things falling into place, and there should emerge some agreement. So I want to now go through some of them, but just very briefly. Now the first thing I would like to mention here just on one slide is this idea of asymptotic safety. I said that most workers believe that something has to happen on the Planck scale, but not everyone, because there's the question of whether standard quantum field theory concepts are actually enough to quantize Einstein's theory. So this approach in some sense is very close in spirit to conventional quantum field theories, RG flows, RG group, and so on, and in fact does not require anything special to happen to the continuum space-time. Somehow I assume that you can go as much as you like below the Planck scale. So here one hypothesizes that there's a non-trivial, non-Gaussian fixed point, and this really means, if true, that the non-renormalizable perturbative quantum gravity is really renormalizable in disguise, because there's some in this infinite dimensional space of couplings, there's a hypersurface to which things can flow. And so in fact, you would just have to fix a finite number of parameters rather than an infinite number of them. So the aim is then one constructs a scale-dependent effective action. One can discuss in some detail what this means, because in a generally covariant theory, the measure of length, etc., it's something that's not fixed a priori. So this requires some rather sophisticated assumptions. But this approach is essentially agnostic about the microscopic theory. It's essentially just the renormalization group equation and what you put in as initial condition, and then the hope is that maybe these things fall in universality classes. What would be observable here? Well, we don't see running Newton's coupling constant when we look outside the window. So all of this is going to take place after the Planck scale, which is here thought to be analogous to lambda QCD. So observable effects would be very hard to come by. The only thing I can imagine is somehow that, in this way you can predict that there should be a small cosmological constant at large distances. But this remains a hope. So let me now say a few words about canonical quantum gravity, because this is the first serious attempt to tackle the problem. And that was actually the first non-perturbative attempt, which was also background independent, which is a direct attack on the Einstein theory in terms of textbook methods of quantizing. Now, what you need to do here is, of course, you have to give up manifest space-time covariance by a split of space-time into space and time, so that space-time geometry can be viewed as an evolution of spatial geometry in time according to Einstein's equations. Geometric dynamics then is defined as follows. The dynamical degrees of freedom are the spatial components of the metric. The components with a time index are Lagrange multipliers. They lead to constraints and their associated canonical momenta. And then the dynamics is defined by the constraints, namely Hamiltonian constraint that goes with time reparametrization invariance, and the spatial diffeomorphisms are associated with the spatial diffeomorphism constraints. Now, the general covariance of the theory in the classical context is in this constraint algebra, which is more complicated, but I've suppressed all indices. But the difference between this and the standard gauge theories, that the dynamics is somehow encapsulated in this Hamiltonian constraint. So what you would do in this approach is to replace this by a functional differential operator. You express everything in terms of operators, and then when you express the Hamiltonian constraint, you get the famous Wheeler-DeWitt equation. This equation has been around for, well, almost 60 years. Nobody to this date has been able to make any, full sense out of it, because it's ill-defined even by the sloppy standards of physicists. And in particular, what you would have to satisfy, you would have to say what becomes of this algebra as you replace classical variables by quantum operators. And as we know from many examples, you would expect anomalies, just like in the case of two-dimensional diffeomorphisms, where the Witt algebra becomes the Virasoro algebra. And in 4 dimensions, you would expect even more drastic modifications. And I'm just saying this because classical space-time covariance in this theory would be replaced by quantum space-time covariance, just like one has a very concrete example how this could happen, but it's something that you have to prove. And this has proved to be impossible, or at least not. There's no solution that people agree on. There have been proposals, of course. So this whole Wheeler-DeWitt program came to a halt because no one was really able to make progress on this. And it got a new impetus with Ashtekar variables, which is a switch to another set of canonical variables. which are essentially the following. It's like in quantum mechanics when you replace Q and P by creation annihilation operators, Q plus I, P. So here you have the spatial spin connection. This is the extrinsic curvature. This is essentially the canonical momentum with a parameter which was later called Barbero-Amici parameter. And originally this was plus minus I. And then he was able to show, Ashtikar was able to show that you have a new canonical pair. And what he was also able to show for gamma equals plus minus I, that in this case the constraints, canonical constraints, take a simple and rather nice form. In particular, it turns out that everything that depends on this variable does so via this curvature tensor, which we know this is just the Yang-Mills field strength associated with SU2. So it's almost like the phase space of Yang-Mills, the SU2 Yang-Mills theory, except that you have two more constraints. That these are diffeomorphism and Hamiltonian constraint.
What does the approximately equal to zero mean?
Oh, weakly zero. You can put it weakly zero in the Dirac. This is the Dirac notation. Now, I think originally it was plus minus I. Later, people put this to a real constant, and I should say, in my opinion, this is where this whole subject took a wrong turn, because once you make this real, then the nice form is destroyed. You get some rather ugly extra term that is very hard to handle. Anyway, the modern version of this is loop quantum gravity, where you don't work with a connection, but with a path-ordered exponential. Holonomy along some edge, and the conjugate variable is the flux, defined like this in terms of this E variable, and then your wave functionals depend on these holonomies. A new feature is that the kinematical Hilbert space can be defined, but it's non-separable, which is kind of weird. But you should keep in mind that all the physical, new physics that is claimed to be associated with loop quantum cosmology, which is a mini superspace version of loop quantum gravity, analogous to the old mini superspace of Wheeler-DeWitt. All the new physics really comes from this non-separability. This is one of the reasons they don't see divergences, because normally you would put here a delta function for this in quantum mechanics. So when you square this, then you have the usual difficulties. But here this difficulty doesn't appear in this form. So this is one of the reasons they so far cannot see ultraviolet divergences, hence no anomalies. And the other peculiar feature is that although you're working with connections, there are no negative norm states. And this has to do with this non-separability.
Herman, have they tried to construct Yang-Mills theory?
No, it hasn't. This program has not led to any kind of valuable new insights for Yang-Mills theory.
But it should be a simpler theory, and we know.
Yes.
So why is this going to work?
Well, I will not say anything on this. I just present the facts. Okay, now the crucial, much of this is just kinematics, defining state space, it's scalar products, it's just kinematics. The core question in canonical gravity is the Hamiltonian. First of all, can you define it, and then can you do anything with it? And I will not describe this in detail, because this is a rather elaborate formalism, was mainly developed by Thomas Thiemann. And this is claimed to be a main success, namely that the Hamiltonian can be defined rigorously as an operator on this kinematical Hilbert space. By the way, this is the ugly term that nobody talks about and which would vanish if you put gamma equal to plus or minus I. This is a little bit like the Migdal formulation of gauge theories, where you just allow yourself to work with field strength and so on. Now, the proper definition is rather intricate. And the one thing I would maybe raise here, because this is a valid question, the question is whether Hilbert space is really the right concept. Because what you find here is more, you need to go to some kind of distribution space. And it's also the question when you're talking about the wave function of the universe, does it make sense when you calculate scalar product? Does this make any sense? Or is it such that you need to give up even such things that we take to be granted in ordinary quantum mechanics? Anyway, there's also some argument that this Hamiltonian is not very physical, because what it does, there are these pictures of the spin networks, which I'm sure you've seen. Spin networks are graphs with vertices and edges and things like this. So what the action of this Hamiltonian does, in some sense, it adds what we call spider webs like this. So it doesn't really, yeah.
Question? I mean, we know that symmetric does make sense, at least classically. So we know that somehow in gravity is a background. There is Minkowski or some background which breaks the symmetry. But do this guy who worked basically...
Well, one of the difficulties here is that the metric is represented, because it's like switching from Q to creation and annihilation operator. So the metric is represented by a singular functional differential operator like this, xx, so collide at 2 points. And so in order to define a classical state, you would have to find a size such that this, well, there's ij, I guess, that this is something like, this would be like a classical expectation value, g ij of x. And of course, there are all kinds of difficulties in making this well defined. So this is one of the reasons.
Like in the Wilson loop way of describing the gauge theory, I mean, we have this problem. But in the case of gravity, for sure, we know what these people do. What do they say? That we know that there is a notion of metric in it.
No, they say eventually they will be able to define a semi-classical limit. But all I'm saying is, this is why it's so difficult for them to find a semi-classical limit, because the metric operator is represented by a singular functional differential operator.
So, Herman, if you start with all this formalization, finally, are you able at least to quantize linearized gravitational waves?
You asking, no linearized gravitational waves quantization would require solving this problem first.
Then what they are doing? What
Nothing.
is small for?
They don't really have metric. How can they do fluctuations of it?
It's all recorded here, so let's continue.
You know, there's no time to, because this is just a pointillistic survey, as I said. So let me just summarize a little bit, summary and critique of these.
You can ask all the quantum gravity.
Anyway, the non-perturbative approaches, this is LQG, but something that developed out of his spin foams. I have no time to talk about it, in group field theory. I put the main emphasis not on the things that we like in quantum fields here, but the things that we like from general relativity, which is background independence, although very often what it really is only spatial background independence, because space-time background independence would imply that you solve the Wheeler-de Witt equation, Hamiltonian constraint, so that's not there. So this is a bit kinematical. However, these approaches so far, they're not able to recover the semi-classical limit, but they also do not incorporate essential insights and successes of standard quantum field theory, which I think is a big shortcoming, like anomalies. You see, this is one thing that's usually not emphasized very much. There are tons of quantization ambiguities. So matter couplings, the restrictions that we know to hold in the standard model, like anomaly cancellations for the quarks and leptons, that's a very interesting and very subtle consistency condition, is not seen in these approaches. But as I said, these issues will be hard to settle without a detailed understanding of how standard quantum field theory and the semi-classical limit would emerge from this framework. So let me now move on. Kostas gave a beautiful review of string theory. So this is, just you said poor man's Bourbaki. So this is a poor man's version of Kostas' presentation. So superworld, basic strategies now quite different coming from quantum field theory. There one tackles this perturbative divergences directly by trying to modify gravity at short distances. This is by introducing supersymmetric matter, because fermions have a tendency to cancel bosonic divergences. So this is realized in supersymmetric series. It's also nice because in some sense it gives a raison d'être for the existence of matter in the world. And also there are such things as maximally, if you really want to push the notion of symmetry to the end, there are maximally symmetric point field theories, n equals 8 supergravity, to which I will come back, 11-dimensional supergravity. And then also one can go to supersymmetric extended objects, where the hope is that the point-like singularities due to the point-like interactions are dissolved by blowing up point-like objects to extended objects. So this has led to the superstring, but I would also like to remind that there's a theory called supermembrane theory, which you can think of as a non-perturbative version of string theory, and from it follows this famous matrix model. Now this theory is much harder to deal with than string theory. String theory is basically free field theory on the worldsheet, but here on the world volume this remains an interacting theory, and there's not been so much progress in understanding it. So as Kostas explained beautifully, so I'll just go down the list. Of course, this is a huge subject. It's very much modeled on concepts from particle physics, so there's no problem with the semi-classical limit. However, there's a problem with, say, the formulation beyond perturbation theory. But we now understand that it's not simply a theory of one-dimensional extended objects. There are D-branes, there are M-branes, there are Kaluza-Klein excitations, and what have you. This is one of the big successes, explaining giving a microscopic explanation of black hole entropy, including higher order corrections to this Bekenstein formula. There's all these ideas about holography. Some people think that holography is the key to quantum gravity. I don't quite share that view.
What would be a physical consequence that I might even be able to measure of this formula for the entropy?
Well, this formula has been proven for very ideal extremal black holes. And first of all, you would have to find an extremal black hole in the universe, and then.
But suppose there were an entropy formula for a visible black hole. What could I do with it?
Not much, really, because visible black holes are. Well, the other thing is that the derivation is done in a completely different domain. It's using D-branes the way Kostas.
Same derivation, which is semi-classical and applied to even standard.
No, but I think there is a slight problem here, because the derivation is done in a domain which is far, far away from classical, and then you extrapolate over it, and I don't know, 20 orders of magnitude, and for this you have to invoke supersymmetry and BPS stability. BPS is invoked a lot these days. For doing all kinds of arguments and strings here, but you should keep in mind BPS is light years away from the real world. It's not, of course it remains a challenge to sort of derive this formula or understand it for a real life black hole. Well, anyway, there's a lot of new ideas that are currently being tested, low energy supersymmetry, large extra dimensions, and so on. And of course, I will not say anything about the implications for mathematics, because this is something everybody knows and appreciates, certainly here at IHES. So what are the open questions? Well, string theory has been a massive intellectual collective effort that's been going on for almost 40 years or so. But we're still struggling to reproduce the standard model as is, not some fancy extensions with tons of extra supermultiplets and so on, but just assume, no superparticles are found at LHC. Then what are we going to do here? This is a real challenge. Similarly, it's a struggle to incorporate. There's no nice way to get a positive cosmological constant. Supergravity, superstring theory love negative cosmological constants, but you look outside the window and it turns out to be positive. I will say a little more about maximally extended supergravity, also in connection with finiteness, because the question is, what is the place of this theory here in this whole scheme? So there's been impressive progress, but I would say there's still no convincing scenario for resolution of space-time singularities, certainly not cosmological or space-like. And the question that was posed initially, namely what happens to the space-time continuum at Planck length, is as open as it's ever been. So and the real question is really what is string theory, in the sense that nobody thinks that at the end of the day it will be the way it's done nowadays. You simply assume a classical manifold and then you have these Planck size extended objects and then you quantize them on this classical background. We all think that this is not going to be the final answer. So one thing I would like to emphasize, and this is a little bit a problem with all approaches, is the lack of, there are too many ambiguities. Now I'm a little bit polemical here because here's this well-known number of consistent vacua, which is far too much for what we need. But this is, as I said, this is a bit hushed up. But if you look at trace the ambiguities, quantization ambiguities and so on, you also find that there's similar non-uniqueness in loop quantum gravity, in discrete quantum gravity. By the way, also in asymptotic safety, because I keep hearing these talks. I've heard them now for quite a while, and I always sit there and think, this is working too well, because no matter what they try, they find a fixed point. For example, if you do gravity in 67 dimensions, there's also a fixed point. And I find it hard to believe that this should also work in 67 dimensions. Anyway, so there's all this ambiguity, which is precisely the opposite of what I said. You should try to force your theory to make some kind of statement that can be checked or verified or falsified. So the question is really, does nature pick the right, whatever it is, answer at random from a huge variety of possibilities, or are there criteria to narrow down the number of possibilities? So I think that in order to discriminate between growing number of diverging ideas, better start looking for inconsistencies. Or else, and this is something Gary Gibbons said to me about certain approaches in quantum gravity, he said this is going to remain fantasy if we can't come up with a solution to this problem. So the last part, I would like to go a little bit more in the direction that I like, namely the question of what is the role of n equals 8 supergravity in this. Now, n equals 8 supergravity was in fashion 35 years ago, and then it became out of fashion with the advent of string theory and obvious problems. But it has recently turned out to be it's much more finite than was originally expected. And in fact, up to 4 loops at least, it behaves exactly like maximal Yang-Mills theory. If it were to continue like this, then it would be just as finite as n equals 4 Yang-Mills theory.
Was not proven to be divergent in higher loops? Was not proven?
No.
Yang-Mills is divergent in 6 dimensions.
Well, Yang-Mills is, yes, it's divergent above 4 dimensions. There's a formula that tells you at which dimensions the divergences start. And here the claim is that for n equals 8 supergravity up to 4 loops, when you survey different dimensions, it's exactly the same formula as in Yang-Mills theory. So it could be, it's not ruled out, it's not excluded that it might be finite to all orders. And this is one of the things I now start worrying about as I grow older. Will I ever know whether it's finite or not? I'm not sure. Anyway, there's now an effort towards 5 loops, but as we heard yesterday, this effort seems to be thoroughly stuck, so it's not clear what's going to happen. Interestingly, the difficulties here at 5 loops are somewhat maybe related to a similar phenomenon appearing in string theory, because there as well as 5 loops, there appears a peculiar difficulty to do with the fact that supermoduli space is no longer split, which means you're not allowed to first integrate over the fermionic moduli and then over the bosonic. This is at least the one sentence I understood from Witten's presentation 2 years ago. I didn't understand much more, but so this is not excluded here. But even if it is finite, of course, you can raise the question: what about non-perturbative quantum gravity? What does it tell us about the resolution of singularities? And secondly, is there any relation to real physics? And most people would answer this question in the negative. But I would like to advertise some recent work, which goes back to some observation of 30 years ago, which could become relevant if they really continue not to find new spin 1/2 degrees of freedom at LHC. And it is the following. It's a really very strange coincidence, which is the following. If we count the number of quarks and leptons, 3 generations, there are 48. And this number is the same that appears in supergravity when you take the 56 fermions, spin 1/2, remove 8 Goldstinos to break all the supersymmetry. It's the same number. And furthermore, the following strange coincidence: if you break the SO8 of n equals 8 supergravity to SU3 cross U1, these are the representations you get for the SU3. And this was an idea of Gell-Mann's, really strange. I would never had such an idea, but he described it as a last-ditch effort to salvage n equals 8 supergravity. So he took the standard color assignments for the quarks and leptons, and then furthermore assigned these quarks and leptons to representations of a family SU3. So this is a new symmetry that acts horizontally among the generations in this peculiar way here. And when you work it out, it's exactly the representations that appear upon making this decomposition of the n equals 8 fermions. And this is also a little bit curious. I think it just indicates one should start looking in unusual directions, because one thing you see here, that this SU3 family would not commute with the SU2 weak, because it puts the upper and lower components of the would-be electroweak doublets in 3 bar and 3 of this family symmetry. Anyway, there's this strange agreement. And furthermore, if you calculate the electric charges of these particles, so they're given here, and then you calculate what you get from supergravity, it turns out that they're sort of systematically shifted away by 1/6. So it's 1/6 for for the 3 of family, and it's minus 1/6 for the 3 bar. So this has been known for a long time. It's sort of, you think, is this a mirage or is it something real? And in fact, we found already long ago with Nick Warner that this scheme is actually realized at the SU3 cross U1 stationary point of n equals 8 supergravity, gauged n equals 8 supergravity. Now, very recently, we've figured out a way to fix up these charges by deforming the U1, but you have to deform it in a certain way that goes outside of n equals 8 supergravity. So there's no extra motivation to look at even more symmetries, and I think this is really the core of the subject, namely the duality symmetries that were originally discovered by Crémière and Juliard. Because we now believe that these symmetries are more important ultimately than space-time symmetries. And what was realized already long ago is that these exceptional symmetries become bigger as you go down, as you do a dimensional reduction. Dimensional reduction means you drop the dependence on internal coordinates. It's just like in Kaluza-Klein theory. But what also happens here is that by doing this, you transmute space-time, former space-time symmetries into duality symmetries. And if you carry this process to the extreme, all space-time symmetry has disappeared and everything is duality symmetry. And by doing this, you follow this chain. I'm sure you've seen this before. So this is E7 that appears in 4-dimensional supergravity, E8 in 3-dimensional maximal supergravity, and below it becomes infinite dimensional. So this is now what we've been working on with Thibault, for the last 12 years or so. So this is the symmetry that was already conjectured to be in the dimensional reduction to one dimension. Now, long ago, I thought, well, who is interested in one-dimensional reduction? Because the theory becomes essentially trivial. You drop the dependence on all spatial coordinates. But then came this other mysterious hint, namely connection or link with work that was initiated or done by Belinsky, Khalatnikov, and Lifshitz long ago. This is BKL. Their characterization of the singularity. So here's singular Big Bang space-time. And what they hypothesized is that as you approach the singularity, spatial points decouple causally. This is just the horizon problem of inflationary cosmology. And what you get is a continuous superposition of one-dimensional systems in first approximation. So this effectively means there's something like an effective reduction to one time dimensions, as you go closer to the singularity. Or in other words, the true symmetry of the theory becomes only apparent as you go towards the singularity. So this is somewhat analogous to the high energy limit of gauge theories. As you go to higher and higher energies, you see more and more of the symmetries. Maybe I should not... this is another, just to explain the philosophy. I said before that cosmological evolution can be viewed as a one-dimensional motion in an infinite-dimensional moduli space of three geometries. This is what Wheeler called superspace, which is a rather complicated moduli space, and such that the cosmological evolution is really like the motion of a point particle in this infinite-dimensional manifold. This is what leads to the Wheeler-DeWitt equation, the wave function of the universe in Wheeler-DeWitt. This is the space it lives on. But of course, we believe that unification of space-time, matter, and gravitation should tell us that there's something more, and not simply something you just glue to this space, but there should be more unified structure. So the question is whether they can understand the full moduli space and simplify it in some sense by embedding it into group theoretical coset. And this is the proposal that we have been following with Thibault, namely to somehow map this evolution of 11-dimensional supergravity onto a coset space, which is of this type, where this is the hyperbolic Kac-Moody group or algebra E10, which is the maximally extended hyperbolic Kac-Moody algebra. So this is work I've been doing over the last 12 years with Thibault, Merkenot, and Axel Kleinschmidt in particular. So E10, I have no time to tell you what E10 is, but nobody knows what it is, so that's one of the nice challenges. So here's a sort of the way the mathematicians would define it. So it's just Dynkin diagram, generators and relations, a la Chevalier-Serre. But this of course works for finite dimensional Lie algebras in the standard way, no big deal. But it's just, you think just adding a node to the Dynkin diagram doesn't mean very much. But what really happens is an explosion of symmetry. In particular for these algebras, for which the Cartan matrix is indefinite, you have what's called exponential growth. And there's just no way known so far how to have a sort of global description of this algebra, not to speak of the group, that's even more complicated. So we've approached the subject in a somewhat pedestrian manner. I think this is something no mathematician would do because this is just too simple-minded in a way. This is the level decomposition. And the nice thing is when you do this with E10, they pop up the bosonic fields of 11-dimensional supergravity, graviton, three-form, and also their duals. But the explosion you see, this is first three levels. If you go to 28, you already have more than 4 billion Young tableaus of SL. Just to illustrate the monstrosity, the monstrous complexity of this Lie algebra. Because when you try to calculate like structure constants, you get stuck at level 4 or 5. Well, my student Fischbacher he's genius with a computer, tried to go to level 6, but he also failed. And what's worse is no matter how far you go, you're sure that if you continue, it gets even more complicated. Anyway, we as physicists, we're not too worried about this. We just go ahead. And so we've really, with this idea of, mapping the evolution of the cosmological evolution onto such a coset space. So this is exactly what we did, just restricting to the low-level things that we can identify with 11-dimensional supergravity. And on this coset space, well, this is something like the maximal compact subgroup. And then we found agreement under certain conditions, but it's certainly non-trivial, between the supergravity equations of motion and the sigma model equations. And the emergence of space-time here is conjectured to emerge as follows, in the sense that the information that was previously in the space dependence of the fields, of the field theory, now in some sense gets spread all over the E10 Lie algebra. There's no more space-time to start with, there's just the Lie algebra, and in it are all the degrees of freedom that you would like to see in the field theory. But of course, there's a lot more. It's not just this. Because the spectrum here, this level decomposition, when you expand it, it has about the same kind of exponential growth as the string spectrum. So this is the thing I wanted to mention, just because I find this really surprising, because I told you that we had with Christoph Meissner, we found a way to embed this or deform the U1 to take care of to get the correct electric charge assignments for the quarks and leptons. And I said, in order for this, you have to go outside supergravity. But what we put a paper on the net just yesterday, where we show that this deformation is contained in this compact maximal subgroup, which is you can think of as an infinite dimensional extension of the R symmetries that appear in supergravity, SU8, SU16, and so on. And first of all, I find this rather amazing that in order, it would really be striking my mind if in order to link N=8 supergravity to the real world, quarks and leptons, you would have to go to such a fancy infinite dimensional extension of the standard R symmetries and standard duality symmetries. And the other thing I would like to emphasize here, with this, you somehow completely change the picture on how you would get standard model fermions out of a Planck scale theory. And in particular, this symmetry is also chiral. I think there's more than enough room in it to also accommodate the electroweak chiral gauge interaction. So this is something I'm quite excited about, but you should keep in mind, the moment they discover a new spin 1/2 fermion at LHC, we're dead. So at least this proposal satisfies the requirement. It's clearly falsifiable. Okay, so I'm almost finished. So here's once again the philosophy that we've sort of been following with Thibaut, Marc, and Axel. So here's again this space-time diagram, or cosmological space-time. And of course, BKL, of course, was just classical all the way down to the singularity. But of course, everyone knows that, or we expect, something happens at the Planck time. So at that point, you should really cut off the classical part of your manifold and replace it by something else, which was, Thibaut always reminds me that this is the famous objection of Zeldovich to BKL. He said it's all very nice, but after a few oscillations, you're already in the Planck regime, and then can forget about your classical theory. So the idea here is really to sort of take this as a guiding principle by looking for the theory that comes here below the Planck scale that replaces space-time by something else. And here the hypothesis is that it's the E10 over K10 sigma model, possibly, well, certainly quantized, which is something we haven't really done, and also, of course, taking into account the fermions, which I didn't really say much about. Let me conclude. To come back to my initial comment, the strongest argument for quantizing gravity is the incompleteness of the standard model and general relativity. And the main question now is, how do we resolve these short distance singularities? And how can it, and of course, should be done in such a way that this resolution can be reconciled with the classical Einstein equations and continuum quantum field theory and so on. And this may happen either by dissolving point-like interactions, like string theory, membranes, and so on. It could happen via the cancellation of ultraviolet infinities. N equals 8 supergravity is a candidate. It could just be then this theory, you go down, there is no divergence. They all cancel. Or is there some fundamental discreteness as something that LQG speculates about? Now, all these modern discrete models like spin foam models and so on, they're all models of discrete quantum gravity, and they all have difficulties in recovering the continuum space-time, and that's the major challenge there. Or is it just the most conservative thing that quantum field theory basically remains valid, but in a version with asymptotic safety? So I would say, just, where do I place my bets? I think symmetry-based approach offers promising perspectives with N equals 8 supergravity, E10. That's absolutely fascinating to me. I've been fascinated by this during all my professional life. But there's still a long way to go. So that's where we are. Thank you.
Thank you. Questions? Slava?
Herman, can you comment on the statement that gravity is equivalent to 2 copies of Young-Mills? Or it's supergravity which is equivalent?
Well, there are various versions. There's the kind of obvious version of it in string theory, because you build closed string states out of left and right moving open string states, and you put 2 spin 1 to make spin 2. So that has been obvious for 50 years.
Yeah, but now it's in a sense of...
Now in field theory, what these people in N equals 8, Bern and company are doing is this famous color kinematics duality, where they actually, for the Feynman integrands, actually replace the Young-Mills integrand by a gravity integrand. And the procedure is that for the kinematic part, you try to find combinations that also satisfy Jacobi-like identities. And then you simply replace the color factor by the kinematic factor that depends on momenta and polarizations. But this is actually where they're now having difficulties at 5 loops. So it's not clear whether this really works to all orders. So what we had yesterday sounded more like eventually you have to give up on that idea, or if it works, you have to modify it in a somewhat substantial manner.
Okay. Kostas?
In this picture of a billiard movement near a singularity, so how should I think of it for a Schwarzschild singularity? What happens?
Well, that's of course the time reversed picture, but the idea is that the Schwarzschild singularity is also space-like. So as you fall into it, it's a precise. Well, the mixer, you will be stretched and squashed, and I always like to emphasize you will be. I mean, it's squashed to a point ultimately. But this will happen in an extremely interesting way, because before you get there, classically at least, you would be stretched and squashed in many different directions. And of course then ultimately, once you get to the Planck regime, of course the classical theory breaks down, and then you have to invoke whatever the proper quantum...
But will I come out ever?
Not with the Schwarzschild, you just... Of course, what happens in the quantum theory, I don't know. But this is just not known.
There are some recent indication in the work with Philippe Chandler is that the term quartic infermions gives a balanced behavior, but this is... So there is something quantum and fermion within this thing which is still to be explored, understood physically.
Yes.
Do you have a question?
No.
Are there more questions? Michel is raising his hand.
Yes. Even if n equal 8 supergravity is proven to be finite, does it mean it's non-ambiguous?
What do you mean non-ambiguous?
Well, there are certain quantum field theories which are finite but nevertheless ambiguous.
In what sense? You mean there are more than one theory that... has this property.
Well, one example is Chern-Simons theory in 3 dimensions, where you have to work hard to find divergences. However, the answer is not in the theory. I mean, for instance, this long discussion, debate an endless debate about should you find K or K plus G when you make perturbation theory. So, is there something analogous in any?
Well, there are certainly ambiguities here in the sense that the n equals 8 can appear in a gauged version. There are different versions of the gauged supergravity, although the SO8 is almost unique, except for some recently found modification. But what I would like to emphasize here, and this was my last remark, is that if there's any link to the real world, it's not just n equals 8 supergravity. Even with this quark-lepton thing, this seems to indicate, you have to go beyond it in a certain controlled way that's, I hope, controlled by this fancy infinite dimensional duality symmetries.
Okay, let us thank Hermann.